Why can't we accelerate an object to exactly the speed of light? I always find this question incredibly frustrating. Not because it's too complicated, but because the familiar answers we usually hear don't truly satisfy me. People say that as the speed approaches 299,792,458 meters per second, the energy required increases to infinity. They also say the object's mass increases to infinity, as derived from Albert Einstein's special theory of relativity, published in 1905. But to me, those answers feel like someone showing me a curve on a graph and saying it has to go like this, while I still don't understand why nature forces it to behave that way. I don't want more formulas, and I don't need elegant equations. What I want to know is what is actually happening in the physical world when we try to push an object faster and faster. What in a very concrete way is limiting that motion? Because if this is a profound limit of the universe, it must be tied to how time, force, and motion truly operate, not just something that exists on paper. And if we pause here and really think about it, perhaps that question opens up a different perspective. So if we want to understand why there's a limit we can approach forever, but never reach, I think we should set aside the graphs and formulas for a moment and try looking at it very simply. It was 1905 when Albert Einstein published special relativity, along with an assumption that sounds extremely simple, but causes enormous trouble. The speed of light in vacuum is the same for every observer, no matter how they are moving. That number is about 299,792 kilometers per second. I admit I'm not particularly fond of imaginary examples like light clocks, and Einstein used them a lot. But in this case, I have to concede that his photon clock is an extremely effective thought tool. Imagine two parallel mirrors fixed a certain distance apart, with a photon bouncing up and down between them. Every time the photon hits the bottom mirror, we call that one tick of time. If you're at rest with this clock, everything is straightforward. The photon goes straight up, straight down. The path each time is the same, and the ticks are evenly spaced. But now put that clock inside a spaceship, moving at a very high speed, say 90% the speed of light, about 270,000 kilometers per second, and you observe from outside. During the time the photon travels from one mirror to the other, the ship has moved a significant horizontal distance. As a result, from your perspective, the photon no longer travels straight, but follows a diagonal path. And here's the crucial point. The photon must still move at exactly the speed of light, 299,792 kilometers per second. No more, no less. But because the diagonal path is longer than the straight path, the time required for the photon to complete one tick must be longer. There is no other choice. This doesn't depend on technology or the type of clock. It relies solely on geometry and the assumption about the speed of light. From this comes a very uncomfortable conclusion. If you look from outside, the clock on the ship runs slower, not because it's broken, but because time in the moving system really flows more slowly compared to yours. This is no longer philosophy. It is a direct consequence of a measured number and a well-tested assumption, and it is the first piece that leads us to the unbreakable speed of light limit. But at this point, I know you'll react exactly the way I once did. What about real clocks? Clocks in laboratories, wristwatches, especially atomic clocks, things humans have built, measured and tested for decades. Surely they aren't just disguised versions of two mirrors and an imaginary photon. This is where the story takes a more serious turn. Because when you break down a real clock to its fundamentals, you find it is not immune to the argument above. Take a classic mechanical clock, the kind widely used since the 17th century after improvements by Christian Huygens. On a macroscopic level, you see gears turning, second hands ticking, springs expanding and contracting. But if you zoom into the atomic scale, every motion you see is actually atoms interacting via electromagnetic forces. No gears turn in perfect absolute simultaneity. When one atom is pulled or accelerated, neighboring atoms cannot know about it instantly. Information about the change in state takes time to propagate, and in ordinary matter, that propagation mechanism is the electromagnetic force described by quantum electrodynamics, where interactions are carried by photons. Photons do not travel instantaneously. From James Clerk Maxwell's experiments in the 19th century to modern measurements, we know photons always travel at a finite speed. The speed of light, about 299,792 kilometers per second. This means that when one part of the clock begins to accelerate, the command for other parts must travel through a chain of electromagnetic photons, and each photon requires a very small but finite time to go from one atom to the next. At low speeds, this delay is so tiny we don't notice it. So intuition tricks us into thinking the entire clock responds instantly. But that's not physical reality. It's just the limit of human perception. Now place that very real clock on a fast-moving ship, just like in Einstein's thought experiments, or in reality, like GPS satellites orbiting Earth at nearly 14,000 kilometers per hour. From inside the ship, atomic processes still occur normally. Photons are exchanged, electrons oscillate, and the timekeeping mechanism functions. But from outside, you're observing a system where every force-carrying photon must travel longer paths through space-time, along diagonal trajectories, just like the photon in the imaginary light clock. There is no fundamental difference here. The photons in the model and the photons in a cesium atomic clock, the kind used as the international time standard since 1967, all obey the same speed limit. When the entire system moves fast, those photons need more time to complete the same information transfer task. And when force transmission processes are stretched out, the entire operation of the clock, whether mechanical or atomic, slows down accordingly. So when you ask, what about real clocks? The answer isn't real clocks are different, but real clocks have no other choice. They are built from the same atoms, the same photons, and the same physical limits that have been measured and verified for over a century. Once we see that even a real clock, with all its atoms, binding forces, and very everyday mechanisms, cannot escape the same mechanism as the photon clock, the story naturally has to take another step. At this point, the issue is no longer a thought model or a clever illustration. It is a serious statement about how the real world actually works. And here, I cannot avoid the most important question in science. Is there evidence? Or is it all just a beautiful theoretical construct? In science, you can tell a very convincing story. But if you can't measure something in the real world, it remains just a story in the end. If time really dilates, if physical processes really slow down when a system is moving, then that effect must leave clear traces in specific experiments with real equipment and real numbers. Remarkably, we don't need spaceships traveling near the speed of light to test this. As early as 1971, two physicists, Joseph Hafele and Richard Keating, carried out a very direct experiment. They used 4 cesium atomic clocks, accurate to about 1 part per billion seconds per day. First, the clocks were perfectly synchronized while on the ground at the U.S. Naval Observatory. Then some were kept as reference, while 2 others were flown on commercial airplanes around the Earth, one eastward and one westward. The flights lasted several days, at speeds around 900 kilometers per hour, and altitudes near 10 kilometers. When the clocks returned and were placed next to the ones that never left the ground, the result was clear. They no longer showed the same time. The difference was only a few tens of nanoseconds, extremely small, but well within the instrument's measurement capability. More importantly, that difference matched the predictions of relativity exactly, when both the motion effect and the gravitational effect were included. And this was not a fluke. Similar experiments have been repeated many times in the decades since, with increasingly accurate atomic clocks, and the results always return to the same conclusion. Moving clocks run slower. If you still feel unsatisfied, nature provides us with another experiment, one much larger and completely unplanned by humans. In Earth's atmosphere, moonars are created when cosmic rays collide with air molecules at altitudes of about 10 to 15 kilometers. In the laboratory, we know very well that moonars have an average lifetime of about 2.2 microseconds before decaying. With such a short lifetime, without time dilation, most moonars would decay before reaching the ground. Yet in reality, ground-based detectors continuously register large numbers of moonars. When their measured speed, nearly 99.9%, the speed of light, is plugged into the time dilation formula, their observed lifetime increases by exactly the amount needed for them to survive the journey. Once again, the measured numbers match the prediction perfectly. This isn't an experiment designed to prove relativity. This is the universe performing the experiment every day, right above our heads. And if you still feel that experiments with atomic clocks, no matter how precise, carry the flavor of something arranged by humans, nature gives us an even more powerful example that doesn't require any clock at all. This story involves particles called muons, first discovered in 1936 by Carl D. Anderson and Seth Nettermeyer while studying cosmic radiation. In the laboratory, muons are very familiar objects. They are produced in particle accelerators, like those at CERN in Europe or Fermilab in the United States, and their lifetime has been measured with extreme precision. A muon at rest in the lab frame has an average lifetime of about 2.2 microseconds, that is 2.2 millionths of a second, before decaying into an electron and neutrinos. This number is not a vague estimate. It has been confirmed through decades of repeated experiments and is regarded as a physical constant, like the electron's charge or the proton's mass. Now look up at the sky. When high-energy cosmic rays from space collide with molecules in Earth's atmosphere at altitudes of about 10 to 15 kilometers, they produce a shower of secondary particles, including huge numbers of muons. These muons are born at extremely high speeds, typically around 99.8% to 99.9%, the speed of light, or nearly 300,000 kilometers per second. If you use ordinary intuition and the 2.2 microsecond lifetime, the calculation is simple. Even at near-light speed, a muon can only travel a few hundred meters before decaying. Over tens of kilometers from creation to ground, they simply have no chance of making it. But since the late 1940s, ground-based detectors and later experiments at various altitudes have shown something completely counterintuitive. Muons still reach the ground in large numbers, not just a few rare cases, but enough for reliable statistical measurement. The first reaction, and a very natural one, is doubt. Are atmospheric muons different from lab muons? But that doubt quickly collapses when we recall a fundamental principle of particle physics. A particle's intrinsic constants do not depend on where it is created. A muon at CERN and a muon born in Earth's atmosphere have the same mass, same charge, and same proper lifetime. No physical mechanism allows them to be more durable just because they were created a few dozen kilometers higher. So what is happening? The answer goes straight back to time dilation. From our perspective on the ground, these muons are moving at speeds very close to the speed of light. According to special relativity, processes occurring in their rest frame must appear stretched out when observed from outside. The decay process of a muon, though not a human-made clock, is still a physical process with its own rhythm. When you plug the measured speed of these muons into the time dilation formula, their observed lifetime increases many-fold, exactly the amount needed to cover the distance from the atmosphere to the ground. No more, no less. This precise match is not coincidence. It shows that time dilation applies not just to clocks, but to every physical process. From the muon's own perspective, nothing strange happens. It is born, exists for its own 2.2 microseconds, then decays. But because it is moving so fast relative to us, when we observe it, that entire process takes longer. In short, these muons are aging more slowly in our eyes. And when you have accepted that even a fundamental particle, like the moon, can age more slowly, simply because it is moving fast, it becomes very hard to stop the story there. Because at this point, the moon is no longer a quirky exception. It is merely the simplest, cleanest example of a much more general rule. The decay process of the moon is a physical process very clearly described by the weak interaction with a characteristic rhythm. An average lifetime of 2.2 microseconds when at rest in the laboratory, a figure precisely measured since the mid-20th century in experiments at Berkeley, CERN, and later Fermilab. But in the universe, particle decay is not the only process with an intrinsic rhythm. Every chemical reaction, every atomic vibration, every molecular bond is a physical process that unfolds over time. And if you have already seen that high speed slows down a particle decay process, a process governed by fundamental constants, then it becomes very difficult to justify why other processes would be exempt from the same effect. Take a simple chemical reaction as an example, such as the oxidation-reduction reaction in a battery, described by Alessandro Volta at the end of the 18th century. At the microscopic level, molecules collide, electrons shift energy levels, old bonds break, and new bonds form. None of the steps in that chain happens instantaneously. Each step relies on electromagnetic interaction. An electromagnetic interaction, as James Clerk Maxwell pointed out in the 1860s, propagates at a finite speed, namely, the speed of light. If, in a fast-moving system, photons take longer to transmit information and force, then the entire chain of that chemical reaction must slow down, not because the molecules want to slow down, but because they have no other physical choice. And if the chemical reaction slows down, then the next step is almost inevitable. Biological processes, no matter how complex, are fundamentally nothing more than intricate networks of chemical reactions. DNA replication, described by Watson and Crick in 1953. Enzyme activity, the contraction of actin, myosin fibers in muscle, or electrical impulses in the nervous system, all rely on electromagnetic and chemical interactions. There is no biological mechanism that exists outside those laws. Therefore, if the chemical reactions in a fast-moving system are stretched out and slowed, then the biological processes in that system must also slow down accordingly. This leads us to the most famous consequence of relativity, commonly called the twin paradox, seriously discussed since the 1910s following the writings of Einstein and Paul Langevin. I don't like calling it a paradox, because when you look closely enough, there is no contradiction at all. Two twin brothers, one stays on Earth, the other boards a ship moving at very high speed, and then returns. When they meet again, the traveler is younger, not because his biology is special, but because all the biological processes in his body have occurred more slowly compared to the one who stayed behind. From his own perspective, everything remains completely normal. But from the outside perspective, all those processes have been stretched in time. And this is the key point in science. We measure time by counting repeating physical processes, from Galileo's pendulum oscillations in the 17th century to the cesium atomic oscillations, used as the second standard since 1967. If all those processes slow down in the same moving system, then saying time slows down is not a vague metaphorical expression. It is simply a concise way of stating a very concrete reality. No process is privileged. No special clock runs correctly, while the rest of the universe runs wrong. From particle decay to chemical reactions to biological life, everything obeys the same consistent rule. And at this point, it is almost unavoidable that a question with philosophical overtones arises. And I think it is better to confront it directly rather than pretend it does not exist. In the end, does time itself really slow down? Or do only the processes occurring within time slow down? At first glance, this seems like a very profound question, but it is precisely here that many people begin to go astray, because if you are not careful, you quickly leave the realm of experimental physics and step into the land of metaphysics, where there are no longer numbers, no experiments, and no way to verify anything. Personally, I have little interest in that kind of debate. In science, we have only one tool for talking about the world, and that tool is measurement. We have no way to access or manipulate something called pure time if it exists separately from physical processes. The only thing we can do is measure time through something that is happening. Since the 17th century, Galileo measured time with a pendulum. In the 20th century, we measured time with quartz crystal oscillations. Since 1967, the official definition of a second has been tied to 9,192,631,770 cycles of the radiation emitted when a cesium-133 atom transitions between two hyperfine energy levels. In every case, time is always defined through a repeating physical process. No process, no clock. And without a clock, the concept of time in science becomes empty. So when someone asks me whether time really slows down or not, the most honest answer is it depends on what you mean by the word time. If you are referring to an abstract flow that exists independently of everything in the universe, then science has nothing to say about it. We cannot measure it, cannot test it, and cannot experiment with it. But if you use the word time in the way science has always used it, that is, the rate of measurable physical processes, then the answer becomes very clear. We have seen photon clocks slow down in Einstein's 1905 argument. We have measured cesium atomic clocks run slower by a few dozen nanoseconds in the 1971 Haffley Keating experiment. We have observed muons with a laboratory lifetime of 2.2 microseconds, but lasting many times longer in the atmosphere when moving at about 99.9% the speed of light. To date, no measured process, from particle decay, chemical reactions, to atomic oscillations, continues at the same rate in a fast-moving system, while others slow down. If you found such an exception, you would immediately shake the entire structure of relativity. But more than a century after 1905, nature has never given us such an example. Every measurement returns to the same conclusion. From the perspective of a stationary system, every process in a fast-moving system occurs more slowly, and this happens uniformly, without selection. That is why, within the framework of science, debating whether time itself slows down becomes almost meaningless. Science does not need a time entity standing outside measurements. It only needs consistency between what can be observed and measured, and that consistency is telling us something very specific. In a fast-moving system, the rate of every measurable process is stretched. When you say 1 second passes, you are referring to a physical cycle. If that cycle takes twice as long when observed from outside, then for the outside observer, 1 second in that moving system has become longer. You can call this phenomenon clocks running slow, processes slowing down, or simply time slowing down. In science, all those ways of speaking refer to the same measurable content. There is no experimental difference between them. So why can't we go faster than light? Only one important thing is different. Now we know that time is not an immobile background. Since 1905, when Albert Einstein published special relativity, and especially after more than a century of experimental verification, from the 1971 Haffaley heating experiment with cesium atomic clocks differing by a few dozen nanoseconds, to measurements of muons living longer at 99.9%. The speed of light, we have sufficient evidence that the rate of physical processes depends on motion. Before understanding this, people often thought of velocity as a simple number. With enough fuel, you just keep accelerating. This way of thinking is very familiar from everyday experience, where a car can accelerate from 0 to 100 kilometers per h simply by pressing the gas pedal harder. But when entering the relativistic velocity regime, this way of thinking begins to collapse. At this point, velocity is no longer the only variable. Time, the very thing used to measure velocity, has also changed, and therefore the focus of the problem must shift from velocity to acceleration. Acceleration is not an abstract number on a dial. It is a real physical process. To increase the speed of a ship, the engine must generate force. That force must be transmitted through the ship's frame, through the metal structures, down to every atom. In ordinary matter, this force transmission occurs primarily through electromagnetic interaction, described by Maxwell's equations from the 19th century, and propagated by photons at the maximum speed of light, about 299,792 kilometers per second. No signal can exceed that limit. At low speeds, this delay is so small that we can ignore it, treating the entire ship as accelerating simultaneously. But as the ship approaches relativistic speeds, this approximation no longer holds. The force transmission signals must travel increasingly diagonal paths in space-time, while the ship's proper time, the time measured by clocks on board, is flowing more slowly compared to the time of a stationary observer. These two factors combine to produce a very specific, calculable consequence from the outside perspective. The observed acceleration of the ship decreases over time. This is not speculation. In relativistic mechanics, even with constant force in the ship's reference frame, the velocity measured from outside only asymptotically approaches the speed of light without ever reaching it in finite time. From inside, the crew still feels nearly constant acceleration, similar to 1g on Earth. But from outside, each incremental increase in velocity requires more and more time to manifest as a measured number. The result is that velocity continues to increase, but at an ever slower rate. There is no special moment when the ship touches the speed of light. There is only a prolonged asymptotic process, and it is here that the question of faster than light travel changes its nature. It is no longer a question of whether we have enough energy to overcome a barrier, but whether a process can ever complete when the very rate of that process is stretched to infinity. When viewed this way, you don't need an additional separate law forbidding motion faster than light. There is no cosmic police officer standing there saying not allowed. There is only the consistent structure of time, acceleration, and force transmission, measured and verified for over a century, that makes a journey exceeding the speed of light never finish in finite time. In everyday life, we often talk about acceleration as if it were just a neat little number. A car accelerates how many meters per second per second. A rocket gains how many kilometers per second after each second. In 17th century Newtonian mechanics, this way of speaking is perfectly fine, because time is considered absolute and force is assumed to propagate instantaneously. But when we move into modern physics, especially after what we learned from special relativity in 1905, that understanding begins to reveal a major flaw. Acceleration is not some number floating in the air. Acceleration is a real physical process, and it only exists when force is transmitted through space and time. Without force, there is no acceleration, and without force transmission, that force cannot produce any effect whatsoever. Think of a modern spacecraft, such as the Apollo ships of the 1960s, or today's Falcon 9 rockets. When the engine at the rear produces thrust, it does not make the entire ship decide to accelerate all at once. The force first acts on the engine chamber, then gets transmitted through the ship's structure via material connections. At the microscopic level, this force transmission occurs through electromagnetic interactions between atoms. Atoms are bound together by electrons and electromagnetic fields, and when one atom is pulled or pushed, it affects the neighboring atom through electromagnetic signals. In the language of modern physics, electromagnetic interaction is mediated by photons, the force-carrying particles accurately described by quantum electrodynamics since the mid-20th century. Photons do not transmit force instantaneously. From James Clerk Maxwell's equations, published in 1865, to countless subsequent measurements, we know that photons always travel at a finite speed, precisely the speed of light in vacuum, about 299,792 kilometers per second. That means even in a seemingly perfectly rigid solid object, a change in state never propagates simultaneously throughout the body. It always requires a very small but finite amount of time to travel from one point to another. At low speeds, this delay is on the order of nanoseconds or picoseconds, small enough that we can ignore it without any problem. But when a ship begins moving at relativistic speeds, approaching the speed of light, this limit can no longer be disregarded. At that point, internal force transmission within the object begins to be directly affected by time dilation. The force-carrying photons are not only limited by the speed of light, but they also have to travel longer diagonal paths in space-time, just like the photons in Einstein's light clock. At the same time, the proper time of the moving system, measured by clocks on board the ship, passes more slowly compared to the time of a stationary observer. These two factors combine to produce a very specific consequence. From the outside perspective, the internal force transmission process occurs more slowly. This leads to an important conclusion that is often overlooked when discussing acceleration. The acceleration that the engine produces in the ship's frame is not reflected externally at the same rate as in Newtonian mechanics. From inside, the crew still feels the force, just like the familiar 1G sensation on Earth. But from outside, the entire chain of force transmission is stretched in time, causing the observed acceleration to decrease as velocity increases. This is not some mysterious proposition. It is a direct consequence of the fact that acceleration is a process requiring force transmission, and force transmission is limited by the speed of light. There is no shortcut for force, no way for a signal to get ahead of light and adjust the entire object instantly. When you view acceleration this way, it is no longer a simple number. It becomes a specific chain of physical interactions, unfolding in time and governed by the structure of space-time. Now, if we step fully inside that ship and observe everything from the perspective of someone accelerating along with it, the picture looks completely different, and remarkably nothing appears strange at all. This is precisely what confuses many people, because they often expect that as an object approaches the speed of light, there should naturally be some clear warning sign. But from inside the ship, there is no alarm bell, no flashing light, no feeling that you are approaching a cosmic boundary. The person inside still experiences acceleration in a very familiar way. If the engine is designed to produce an acceleration of about 9.8 mesos, what equivalent to the 1 g we feel on Earth's surface, then you will feel the same downward pressure against the floor as when standing still on the ground. That sensation does not change over time, whether the ship has reached 10% or 90% of the speed of light. From your perspective, you are always at rest in your own reference frame. The clocks on board continue to tick steadily. If it is a cesium-133 atomic clock, it still counts exactly 9,192,631,770 cycles per second, as per the international definition adopted in 1967. Measuring instruments function normally. Signals from the engine to control systems arrive on time. There is no delay you can directly perceive. If you perform a physics experiment inside the ship, measuring the speed of light, the electron charge, or the oscillation period of a pendulum, you will obtain exactly the same results as if you did the experiment in a stationary laboratory on Earth. This is not a convenient assumption. It is a foundational principle established since 1905. The laws of physics in their local form are the same in all inertial frames, and even in uniformly accelerated frames, they remain consistent at the local scale. No internal experiment allows you to determine your absolute velocity relative to a distant observer, and the same holds for acceleration. From inside the ship, if the engine continuously supplies the same force, the acceleration you feel does not diminish at all. There is no sensation that acceleration is weakening or losing effectiveness. This is the key point. Every argument about acceleration, slowing down, only appears when we switch to the perspective of a stationary external observer. In your own frame, proper time, measured by the physical processes on board, continues to flow completely consistently. Your wristwatch, your heartbeat at about 60-70 beats per minute, the chemical reactions in your body, all remain synchronized with one another. No process runs out of sync with the rest. Therefore, from inside, there is no reason for you to suspect that anything unusual is happening. You do not feel yourself slowing down. You do not feel yourself entering a forbidden zone. You simply feel that you are accelerating, just as in countless other familiar situations humans have experienced since the invention of engines. This very normality is what matters. It shows that no mysterious internal force arises to hinder your motion as you approach the speed of light. There is no cosmic friction, no invisible pressure pushing against the ship. If there is a limit, it is not something you perceive directly from inside. It does not manifest as a new force or a technical malfunction. And that is precisely why our internal intuition so easily leads to the idea that there must be some trick to overcome this limit. But physics does not accept just one viewpoint. It demands consistency across all valid viewpoints. From your position, the ship is still accelerating. The engine is operating exactly as designed, with no sign that the system is malfunctioning. But at the same time, you observe something that has been familiar since 1905. The clocks on the ship no longer tick at the same rate as yours. If the ship carries a cesium-133 atomic clock, which counts exactly 9,192,631,770 oscillations per second, according to the international standard from 1967, then from your perspective, its ticks occur more slowly. This is not a device malfunction. The same effect was directly measured in the 1971 Hafele-Keating experiment, when atomic clocks flown on airplanes drifted by a few dozen nanoseconds compared to ground clocks. This immediately leads to an important consequence for how you observe acceleration. Acceleration, as you measure it from outside, is defined as the change in velocity over a period of your time. But if the corresponding time interval on the ship is stretched longer due to time dilation, then the same internal acceleration process will produce less velocity change per second of your time. In short, the acceleration you observe begins to decrease. This is the part most prone to confusion. From inside the ship, if the engine produces constant acceleration, say 1 g or 9.8 m/s, the crew still feels the exact same pressing force as when standing on Earth. But from outside, each beat of that acceleration takes more time to manifest as a velocity change, because the ship's proper time is slowing relative to your time. If you plot the ship's velocity against your time, you no longer see a straight line increasing steadily as in Newtonian mechanics. Instead, you see an asymptotic curve. Velocity keeps increasing, but the rate of increase gets smaller and smaller. There is no contradiction here, because these two measurements belong to two different reference frames. In relativity, there is no absolute acceleration independent of the observer. Acceleration, like time and velocity, is frame dependent. At low speeds, the difference is tiny. That is why in everyday life, from cars to airplanes, we do not need to care about it. But when the ship approaches the speed of light, about 299,792 kilometers per second, time dilation becomes significant. Each second that passes for you corresponds to less than 1 second passing on the ship. Therefore, in each of your seconds, the ship only completes a smaller fraction of its internal acceleration process. The observed acceleration continues to decrease, but it does so smoothly and continuously. There is no breaking point, no moment when acceleration suddenly vanishes, no new resisting force that appears. The ship does not crash into the speed of light like a wall. Instead, it approaches asymptotically. Each next step requires more time to manifest in your reference frame. And because this process stretches out indefinitely according to the stationary observer's time, the speed of light is never reached. The people inside do not see this because they measure everything with their own proper time, which continues to flow perfectly normally in their frame. You, standing outside, measure the same process with your time, and you see it slow down. Both descriptions are correct. They do not contradict each other. They are simply two different views of the same physical reality. And it is this consistency that makes the picture complete without needing any additional hypotheses or special forbidden rules for faster than light motion. When we place these two parallel pictures side by side, one from inside the ship and one from outside, a rule that is both intuitive and profoundly strange begins to emerge. The interesting thing is that you do not need to write down any equation to see it. Simply sticking to the physical logic we have built since the early 20th century is enough. The rule can be stated concisely as follows: the faster you go, the more time it takes to go even faster. Stand in the position of the stationary external observer, as in the classic analyses originating from Albert Einstein's 1905 paper. This observer sees the ship undergoing constant proper acceleration in its own frame. For example, a constant 1 g or 9.8 m/s. In the early stages, when the ship's speed is still very small compared to the speed of light of 299,792 kilometers per second, everything happens almost exactly according to the Newtonian intuition that Isaac Newton described in 1687. Each second, velocity increases by nearly a constant amount. Nothing special. But when the ship's speed reaches values like 0.5 c, then 0.9 c, the difference between the ship's time and the observer's time becomes noticeable, just as measured in the 1971 Hathaway Keating experiment, or in measurements of muons moving at 99.9% the speed of light. Each second of the external observer now corresponds to less than 1 second passing on the ship. That means that in the same interval of observation time, the ship completes fewer beats of internal acceleration. The result is very simple, but very profound. Each subsequent increase in velocity requires more observation time to occur. Not because the engine weakens, not because the force disappears, but because the very rhythm of the process that produces the velocity change is being stretched. You can picture this without mathematics by thinking of an atomic clock on board that runs slower relative to your clock. If in each oscillation cycle, for example, 9,192,631,770 cycles of cesium-133, the ship gains a little more velocity, then as those cycles stretch out in your view, the velocity increments stretch out accordingly. At first, when the ship's clock runs nearly in sync with yours, the velocity increments happen quickly. But as that clock slows, you have to wait longer to see the same amount of change. The closer you get to the speed of light, the stronger the time dilation becomes, and the longer you must wait to see any further velocity change. What matters is that there is no special threshold at which the universe slams the door shut. There is no sudden moment. Everything happens smoothly and continuously. Each time the ship gets a little faster, time dilation increases a little more. Each time time dilation increases, the effectiveness of the observed acceleration decreases a little more. This is a self-reinforcing logical loop. Going faster makes the ship's time slower. Slower time makes each acceleration step require more observation time. And because each acceleration step requires more time, going even faster becomes increasingly difficult from the external viewpoint. There is no contradiction in this chain. It reinforces itself. And this is why the speed of light is never reached in finite time from the stationary observer's perspective. To reach the speed of light, you would need to complete an infinite number of velocity increase steps, but each subsequent step demands more time than the previous one. You can get very close, but the time required to go just a little farther is always pushed further into the future. From inside the ship, this does not contradict anything, because the people inside measure everything with their proper time, and in that measure, each acceleration step still occurs steadily. But relativity shows us that a process can be perfectly normal in its own frame while being stretched out to infinity in another observer's frame. And that is exactly what is happening to acceleration as velocity approaches the speed of light. Acceleration does not disappear. It is not canceled. It is merely spread thin across observation time. The result is that the velocity curve versus the stationary observer's time flattens more and more, approaching the speed of light ever closer without ever touching it. Simply accept three things that have been measured for over a century. Time dilates as velocity increases. Acceleration is a process that takes time, and no signal can exceed the speed of light. And the conclusion almost appears by itself. The faster you go, the slower you get in the observable sense. Ever since Albert Einstein laid the foundation for special relativity in 1905, and after more than a century of experimental verification, it has come to resemble a horizon more than anything else. You can approach it forever, but you can never reach it in any finite time from any external observer's perspective. There is no special moment when the ship hits the speed c, that is approximately 299,792 kilometers per second. No bizarre physical event occurs precisely at a speed of exactly c. The only thing that happens is an ever more pronounced asymptotic process. Each time the ship gets a little faster, the time dilation factor, confirmed by the Keating experiment in 1971 and muon measurements since the 1940s, increases a little more. And each time time dilation increases, the acceleration process, as viewed from the stationary reference frame, gets further stretched out. The result is that the observed acceleration gradually freezes, not in the sense that it disappears completely, but in the sense that it becomes increasingly ineffective at producing changes in velocity over the observer's time. You can still measure acceleration, but its impact on velocity becomes smaller and smaller. Imagine you are watching a video of the ship accelerating, and every time the speed gets closer to sea, that video gets played in slow motion a bit more. At first, this slowdown is very slight, almost imperceptible, but when the ship reaches speeds like 0.9 c or 0.99 c, the effect becomes obvious. Changes that previously took a few seconds now require minutes, then hours, then even longer to appear on your screen. You will never see a single frame in which the ship touches the speed of light. You only see that between each frame, the change in velocity gets smaller and smaller, while the time interval between those changes gets longer and longer. This is the real meaning of saying that the speed of light is an asymptotic limit. It is not a destination, but a boundary that the approach to it takes infinite time. Acceleration from the outside gradually freezes. In this sense, it still exists in the ship's frame, but its ability to produce additional finite velocity over the stationary observer's time gradually approaches zero. This explains why there is no special moment that requires new physical rules. You do not need one set of laws for speeds below c and a different set for speeds above c. You also do not need a mysterious mechanism to prevent the ship from crossing c at some decisive instant, because there is no decisive instant at all. The speed of light is never reached, so there is never a point at which the current laws break and need to be replaced. Everything proceeds smoothly, continuously, and consistently from start to finish. This also resolves a very common misconception. Many people think that when an object approaches the speed of light, it must somehow slow down in a way that the people inside can feel. But as we have seen, from inside the ship, there is no feeling of freezing at all. Acceleration is still felt. Proper time still flows steadily according to internal processes. The freezing only appears in the way the external observer describes that process using their own time. And it is precisely this difference that makes the two perspectives completely consistent. The people inside the ship never see themselves stuck just short of c, because for them there is no absolute notion of approaching the speed of light. They simply see themselves accelerating. Meanwhile, the stationary observer outside sees an acceleration process that becomes increasingly ineffective, stretching out infinitely according to their time. This is the key point. The speed of light limit is not a mechanical barrier or a new drag force that appears at high speeds. It is a consequence of the way time, acceleration, and force transmission, all limited by the speed of light, interweave with one another. When these three factors combine, the result is not a collision, but an asymptote. Acceleration is not forbidden, not destroyed. It is merely spread out so thinly that from the external viewpoint, it no longer produces any additional finite velocity in any finite time. At this point, I know very well that the familiar objection will arise, because I myself asked this very question early on. If the issue is that acceleration gets spread thin over observer time, then why not simply increase the force? In everyday life, that is exactly how we solve every acceleration problem. If a car accelerates too slowly, we press the gas pedal harder. For the Saturn V rocket in the Apollo program in the 1960s, to leave Earth's surface, they burned more than 13 tons of fuel per second to generate enough thrust to overcome Earth's gravity. This intuition is very strong, and there is no obvious reason to think it would fail when applied to near light speed motion. So instead of dismissing it outright, let's seriously follow this logic all the way through. Imagine our ship is equipped with an ideal engine. No overheating, no breakdowns, no technical limits. When the speed is still low, a certain amount of fuel produces a certain acceleration. If from the external viewpoint, the observed acceleration is halved because time on the ship has slowed, then we double the force. If it is reduced tenfold, we increase the force tenfold. At first glance, logically, this plan seems perfect. The people inside would feel greater acceleration, and the stationary observer, after accounting for time dilation using the relativistic formulas Einstein established back in 1905, would again see acceleration as before. Velocity, it would seem, would continue to increase steadily according to the stationary observer's time. But here physics does not allow us to stop at the first step of thinking, because increasing force is not an abstract action. It means something very concrete. The engine must impart more momentum to the ship, and that momentum must be transmitted through the material structure of the ship via physical interactions. Those interactions, as we have seen from James Clerk Maxwell's electromagnetism in the 19th century, and its subsequent developments in the 20th century, are not transmitted instantaneously. They are carried by force-carrying particles, and those particles, in the case of electromagnetic force, photons, are limited by the speed of light, approximately 299,792 kilometers per second. When you increase the force, you are asking the force-carrying photons to transmit more momentum in the same observer time interval. But this same time interval becomes increasingly ambiguous as speed increases, because from the external viewpoint, the ship's time has slowed down. That means to achieve the same level of internal state change in 1 of your seconds, the ship must perform many more internal cycles. And when you increase the force to compensate for that, you make the force transmission process even more severe. The force-carrying photons must transmit more momentum, but they are still bound by the same speed limit and the same stretched space-time structure. The consequence is that as speed increases, increasing force is not a definitive solution, but an endless arms race. You increase force to compensate for time dilation, but that very increase in force must occur in a system where time is flowing more slowly. Therefore, to keep the observed acceleration constant, you cannot just increase force once. You must continuously increase it. Each time the speed increases a little more, the time dilation factor grows larger, and you must increase the force yet again to compensate. There is no finite number that is enough. Each finite increase in force can only compensate for a finite amount of time dilation. But as speed approaches the speed of light, the required time dilation to compensate for increases without bound. In physics, increasing force is equivalent to increasing power, and increasing power is equivalent to increasing energy consumption. This is not philosophical speculation, but a direct consequence of the definitions of work and energy standardized in the 19th century. At first, this energy increase seems moderate, but the closer you get to C, the faster the amount of energy required for each step to maintain the observed acceleration increases, not arithmetically, but in an unbounded trend. And it is here that the notion of infinite energy begins to emerge, but no longer as an abstract slogan. It has very clear physical content to keep the observed acceleration from decreasing as speed asymptotically approaches. C, you must continuously increase force. To continuously increase force, you must continuously increase power. And to increase that power without limit, you need an unbounded amount of energy. Not because some law forbids large amounts of energy, but because the very logic of resisting time dilation leads you to this conclusion. When you follow that logic all the way, there is no escape. You can accept that observed acceleration gradually decreases and asymptotically approaches zero, or you can try to resist it by increasing force. But if you choose the second option, you must accept the inevitable consequence unbounded energy demand. There is no middle path, no technological trick to avoid this. This is not an engineering problem, but a problem of the structure of space-time and the way forces are transmitted. If you continue following this logic to its end, you will realize that we are not turning onto a new path at all, but simply going deeper into the very path opened in 1905, when Albert Einstein first wrote down the consequences of special relativity. When acceleration is spread thin over observer time and approaching the speed of light, approximately 299,792 kilometers per second, becomes an asymptotic process. The next question almost automatically arises: what happens to energy in this process? This is precisely where the familiar answer, infinite energy, returns. But this time, it no longer stands alone. It is tightly bound to the entire picture we have built from time dilation, acceleration, and force transmission. As speed increases, experiments from atmospheric muons in the 1940s to atomic clocks in the Hafele Keating experiment of 1971 all show that the proper time of the moving system slows down. When proper time slows, each unit of internal acceleration, whether 1g or 10g, takes more observer time to manifest as a change in velocity for the stationary observer. If you accept this consequence, the ship will get closer and closer to the speed of light, but each subsequent step requires more and more time from the external viewpoint. But suppose you do not want to accept that. Suppose you say you want to keep the observed acceleration from decreasing, for example, always at 9.8 m/s² in each second of the stationary observer's time. Then your only option is to increase the force. Acceleration is the result of force, and if the effectiveness of force is reduced by time dilation, the only way to compensate is to increase the force accordingly. But in physics, increasing force is not an abstract command. It means the engine must deliver more energy to the system, must perform more work in each observer second. The physical interactions inside the ship, transmitted by photons, according to the laws described by Maxwell in the 19th century and perfected in 20th century quantum electrodynamics, must carry more momentum in the same time interval. And all of this occurs in a special context, the context in which the proper time of the system is stretched relative to the stationary observer's time. At low speeds, the energy cost to compensate for time dilation is so small that you barely notice it. You increase the force a little, and the observed effectiveness returns almost to normal. But as speed increases, each such compensation puts you in a new situation where time dilation is stronger than before. And because time dilation is stronger, you must increase the force even more if you want to keep the observed acceleration from decreasing. There is no point in this chain where you can stop and say that's enough. Each finite level of force only compensates for a finite amount of time dilation, but the required time dilation to compensate for increases without bound as speed asymptotically approaches the speed of light. When you follow this logic to its end, the demand for increased force does not increase linearly, but in an unbounded trend. And since force is produced by consuming energy, the energy demand increases in the same way. This is when the concept of infinite energy appears with its full physical content. It is no longer an abstract statement derived from an equation, but a conclusion forced by the way acceleration, time, and force transmission are intertwined. You can choose to supply a finite amount of energy. In that case, the force you produce is finite. The observed acceleration will gradually decrease, and the ship's speed will asymptotically approach the speed of light over infinite observer time. Or you can try to resist that decrease by continuously increasing force. But if you choose this path, you must accept that each increase in force only brings you to a point where the next required increase is even larger. No finite amount of energy is sufficient to complete the process in finite observer time. It is here that older expressions like mass increases to infinity, which appeared in early 20th century textbooks, begin to be understood more correctly. It is not that the object itself becomes infinitely heavy in an intrinsic sense, but that the energy required to continue changing its state of motion over observer time increases without bound. When viewed this way, everything becomes coherent. Time dilation causes observed acceleration to decrease. To resist that, you must increase force. Increasing force requires increasing energy. And as speed approaches the speed of light, the required energy level has no limit. There is no mysterious leap in this chain of reasoning. Each link connects directly to the one before it. When you put all these pieces together, from Albert Einstein's special relativity of 1905, atmospheric muon measurements from the 1940s, to the Hathaway Keating atomic clock experiment of 1971, the question of faster-than-light motion begins to change shape entirely. It is no longer the question, what are we missing, but becomes, what are we misunderstanding? Many faster-than-light ideas throughout the 20th and early 21st centuries often focused on the engine. If the engine is powerful enough, if the thrust is great enough, if the power is high enough, then surely we could exceed the 299,792 kilometers per second limit. But as the analyses based on the very measurements have shown, the problem does not lie in whether the engine is weak or strong. You can assume a completely ideal engine, no wear, no overheating, no technical limits, capable of increasing thrust arbitrarily. Even in that most generous scenario, the physical logic remains unchanged. Each time you increase force to compensate for time dilation, you pay with a larger energy requirement, and that required energy level increases without bound. As speed approaches c, so is the problem with materials. Is the hull not strong enough to withstand tens or hundreds of Gs over long periods? In real engineering, this is certainly a major obstacle, as NASA's studies on high acceleration materials from the 1960s have shown. But even if you assume perfect materials, no deformation, no melting, no collapse under any acceleration, the conclusion remains the same. There is no moment when the universe says, your materials can't take it anymore. The limit appears long before you even need to worry about that. This shows that the failure of faster than light is not a failure of technology in the usual sense, like not having jet engines in 1900 or powerful enough rockets before 1957. It is a failure at a deeper level, at the structural level. It lies in the way time operates and the way forces are transmitted in the universe. Acceleration is not an abstract number that can be increased indefinitely by turning up the knob. Acceleration is a physical process, and that process requires time to occur. Force is not an instantaneous command, but an interaction transmitted through force-carrying particles, photons in the electromagnetic case, as James Clerk Maxwell described in the 19th century and precisely verified in 20th century quantum electrodynamics. Those force-carrying particles, without exception, are all bound by the speed of light. When you try to push an object faster and faster, you are not just changing its velocity. You are placing the entire force transmission structure of that system into a context where its proper time is stretched, exactly as modern atomic clock measurements, with errors of only a few parts per billion, have confirmed. Every microscopic interaction, every momentum transfer from engine to hull must occur in a space-time that is being lengthened, and therefore those interactions take increasingly more observer time to produce the same effect. This is where faster than light truly fails, not because we are not smart enough to build a better engine, but because we are demanding that a physical process complete, while the very rhythm of that process is being slowed down. You are trying to force interactions to happen faster than light, while every mechanism that allows interactions to exist is limited by light. That is not a minor glitch that can be fixed with a clever idea. It is a structural contradiction. That is why so many faster-than-light ideas, when examined closely, must covertly assume instantaneous transmission of information, a force acting simultaneously on the entire ship, or a control signal with no delay. But each time you remove those assumptions and force the idea to obey the principles verified over more than a century, the finite speed of light, delatable time, forces that require time to propagate faster than light collapses. Not because the universe forbids it arbitrarily, but because it demands a space-time structure different from the one all measurements from 1905 to the present have confirmed. In short, to achieve faster than light motion in the usual sense, you do not just need a new ship or a new engine. You need a new universe. Once it becomes clear that faster than light travel doesn't stumble over engines or materials, but over the very structure of time and the way forces are transmitted, another consequence emerges almost immediately, even without needing to dive deep into the mathematics to recognize it. That consequence is causality. I only want to touch lightly on this point, just enough for you to see why the universe seems so insistent on not allowing motion faster than light. At its simplest, causality is the idea that cause precedes effect. You press the button, then the light turns on. You burn fuel, then the ship accelerates. This order seems so obvious that from Isaac Newton's 17th century all the way to today, we tend to take it for granted. But things started getting subtler in 1905, when Albert Einstein showed that time and space depend on the frame of reference. At that point, the notions of before and after were no longer absolute for all observers. In relativity, two events separated in space can be ordered differently by observers in different states of motion, as long as those events cannot influence each other via signals traveling at or below the speed of light, about 299,792 kilometers per second. And here is the key point. The speed of light is not just a number measured in the Michelson, Morley experiments of the late 19th century, or in modern laser measurements. It acts as a causal boundary. It separates events that can have a direct cause, affect relationship from those that cannot. If I cause an event here, the earliest its influence can reach somewhere else is only after light, or a slower signal, has had time to travel there. This ensures that in every valid reference frame, everyone agrees on the basic causal order. A cause never appears after its effect. But suppose you allow a signal or an object to travel faster than light. Then that boundary is breached. Immediately, you can connect two events such that for some observers, the effect occurs before the cause. This is not a philosophical game. As early as the 1910s, 1920s, when physicists like Hermann Minkowski and later Einstein analyzed the structure of space-time, they saw that if faster-than-light signals existed, then in one frame event A could cause event B, but in another frame B would appear before A. And so you fall into a deeply unacceptable situation. An effect appears before its cause has occurred. You don't even need to invoke science fiction time travel scenarios. Merely allowing information to influence an event in the past of some observer is enough to make causality ambiguous. What matters is that the universe we observe shows no sign of tolerating such ambiguity. From fundamental particle experiments in the second half of the 20th century to modern astronomical measurements, every observation is consistent with a picture in which physical influences propagate in a way that preserves causality in every reference frame. Light, with its finite speed, acts as a gatekeeper. It ensures that if one event can influence another, then everyone, regardless of how they are moving, agrees that the cause happens before the effect. Looking back at the arguments about acceleration, time dilation, and energy, you see that the speed of light limit is not an annoying technical detail. It is part of a larger structure in which space-time is organized to protect causality. If you try to cross that limit, you are not merely asking for more energy or a better engine. You are asking the universe to allow influences to propagate in ways that break the cause-effect order. And the universe, at least the one that every measurement from the early 20th century to now has confirmed, appears to refuse that request. What is remarkable is that you do not need to posit a separate ban on faster-than-light travel to avoid causal paradoxes. Simply keep the existing laws consistent. The speed of light as the limit for information transfer, time as dilatable, and all inertial frames equally valid, and faster than light is automatically excluded. It is not shut out by a slamming door. It simply has no place to stand in this picture. This universe does not behave like a strict legislator issuing arbitrary prohibitions. There is no sign posted at 299,792 kilometers per second reading, "Do not cross." There is no secret clause hidden by Einstein in his 1905 paper saying that if you dare exceed a certain number, the universe will punish you. What is happening is far more subtle. The universe is merely consistent with itself, and that very consistency, when followed all the way through, forces you to accept unavoidable consequences. The speed of light is not an externally imposed limit. It is a number that emerges naturally from the structure of space-time and the way physical interactions propagate, something confirmed from the Michelson-Morley experiment of 1887 to modern laser measurements with errors smaller than 1 part per billion. When you accept that information cannot travel instantaneously, that time does not tick at the same rate in every frame as atomic clocks have clearly shown since the 1970s, and that forces require time to act through light-limited carrier particles, then the limit appears automatically. You do not need to add a new law to forbid faster-than-light travel. You only need to keep the existing laws from contradicting each other. This often disappoints people because it offers no clear villain to blame. There is no light drag force, no cosmic wall discovered in any experiment from the 20th century to the present. Only a very tightly woven network of relations between time, space, and energy. When you pull on one thread in that network, for example, by allowing signals faster than light, every other thread must adjust, and the entire structure begins to contradict measurements that have been repeated thousands of times in laboratories and across the cosmos. Faster than light fails not because it is forbidden, but because trying to insert it forces you to break one of the foundational links. Either allow instantaneous information transfer, or allow causal order to reverse, or allow a process to complete while its proper time is stretched to infinity. And each of those choices directly contradicts what we have verified about the world, from muon decay to the everyday functioning of GPS. This same consistency also explains why modern physics does not need to patch itself with exceptions. There is no line in relativity that says everything holds until you reach the speed of light, and then from here on it's different. Instead, the laws are written so that they automatically handle the limit. As you approach the speed of light, effects like time dilation and acceleration degradation grow stronger automatically, ensuring you never reach the limit in finite time in any valid frame. No shock, no breaking point, just a smooth but unrelenting transition. In a way, this is the beauty of modern physics. It needs no rigid commandments, only consistency. Once you grasp that, you begin to see that many questions of the form, "Why doesn't the universe allow this?" can really be answered with another question. Because if it did, the universe would no longer be itself. Space-time would lose the structure that keeps causality consistent. Measurements would no longer agree, and what we call events would lack a shared order that all observers could accept. The universe we know, one confirmed by more than a century of precise measurement, does not operate that way. It operates by ensuring that everyone, no matter how they move, can still tell the same basic story about cause and effect. And the speed of light is an essential part of that storytelling mechanism. It sets the boundary for what can directly influence what, and by doing so, keeps the story from becoming tangled. Importantly, this perspective does not make physics pessimistic or restrictive. On the contrary, it shows that the limits we encounter are not signs of insufficient technology, but signs of a profound and coherent structure, one that has allowed science to function reliably from Newton's time, through Einstein, to today. Looking back over the entire path we have traveled, what stands out is not the number of hypotheses or the complexity of the arguments, but the astonishing simplicity of the starting point. Everything flows from a single principle, clearly stated by Albert Einstein in his 1905 paper. The speed of light in vacuum is the same for every observer, not approximately the same, but exactly the same, measured at 299,792,458 meters per second. Whether you are at rest, moving uniformly, or accelerating. At first glance, this principle seems harmless, even slightly counterintuitive. But when experiments from Michelson, Morley 1887, to modern 21st century laser measurements keep confirming it with errors smaller than 1 part per billion, you are forced to take it seriously. And once you do, a whole cascade of consequences unfolds. First comes time dilation. If the speed of light is invariant across frames, time and length cannot remain the same for everyone simultaneously. This is not philosophical inference. It is a conclusion measured directly with cesium atomic clocks in the 1971 Heffele-Keating round-the-world flights, where moving clocks lag by exactly tens of nanoseconds compared to stationary ones. Once time depends on motion, every moving clock must run slower, as seen from outside, not just photon clocks in thought experiments, but real clocks, because every physical process relies on finite speed information transfer and interactions. From there, acceleration changes its role. It is no longer an abstract number, but a process that unfolds in time. When a system's proper time is stretched, its observed acceleration diminishes, an effect described quantitatively in relativity and indirectly verified through near-light speed particle beams at CERN since the 1960s. Add the fact that forces take time to propagate. Force-carrying particles cannot exceed the speed of light, and the picture closes. Every time you try to accelerate further, you are working within a system whose internal rhythm is slowing in the eyes of an outside observer. Thus, approaching the speed of light becomes an asymptotic process, not a journey with a destination. You can get very close, but each next step requires ever more observed time. If you refuse to accept that, and want to keep observed acceleration constant, you must increase force, that is, increase energy. But as time dilation grows without bound, the energy required to compensate also grows without bound. This is where the notion of infinite energy appears as a logical consequence, not an imposed condition. And if you try to cross the limit with faster-than-light motion, you immediately collide with causality. The cause-effect order preserved by the light speed limit begins to waver as mid-20th century analyses of causal paradoxes showed. What is remarkable is that no additional prohibitive law is needed. Simply hold fast to the initial principle, the invariance of the speed of light, and let the remaining laws unfold. When you do, time dilation emerges, the acceleration limit emerges, and the impossibility of faster-than-light travel emerges, inevitably, without breaks, without changing the rules midway. From what seems like a simple principle, you arrive at a picture where time is not absolute, acceleration is constrained, and the speed of light becomes an impassable horizon. To me, this is one of the deepest lessons of modern physics. A single correct principle, when applied consistently, can govern an entire universe of phenomena. One principle, many consequences, and all of them are merely different ways the universe keeps its story from contradicting itself. The inability to go faster than light does not make the universe poorer or less fascinating. On the contrary, it makes the universe more worthy of respect. Since 1905, when Albert Einstein published special relativity and set the speed of light at the invariant value of 299,792,458 m per s, we have had more than a century of measurement, verification, and dialogue with nature. From the Michelson-Morley experiment of 1887 to cesium atomic clocks differing by mere nanoseconds on 1971 flights, to particle accelerators at CERN in the latter half of the 20th century, nature has always answered consistently. There is no sign that it is stingy for not permitting everything we can imagine. In fact, a universe in which everything imaginable could happen, with no deep constraints, would be a very shallow universe. What makes this world interesting is not the number of open doors, but the tight structure standing behind those doors. When you know the speed of light is invariant, that time can dilate so much that muons live 10 times longer while plunging toward Earth. That acceleration cannot keep increasing indefinitely without demanding ever greater energy, and that causality is preserved in every frame. You are seeing a universe with profound internal order. I do not see here a reminder that humans are small or powerless. I see a reminder that we live in a structured world where everything has a reason, even if that reason sometimes runs counter to our desires. The inability to reach the speed of light does not mean we lack intelligence or creativity. It means there are principles deeper than any technology, and that does not kill imagination. It gives imagination a solid foundation. Within the very framework of these principles, there remain countless wonders, curved spacetime, as in the 1915 general relativity, mass-energy equivalence via E = mc², virtual particles appearing and vanishing in times as short as 10 seconds. Compared to those, the inability to go faster than light does nothing to impoverish our imagination. It merely reminds us that the best imagination is one that respects reality. Science does not say don't dream. It says dream honestly, ask questions, listen to the answers, then adjust your understanding. When we do that, every new discovery is not merely a technical victory, but a step forward in a long conversation with nature. And in that conversation, respect arises, not fear, not blind worship, but respect for a consistent structure in which every piece has its role. Seen this way, faster than light is not like a door slammed shut. It is like a path that never existed on the map. That does not make the map poor. It makes the map honest. There is a very quiet beauty in realizing that not everything imaginable can happen, and that what can happen is already rich enough to fill many lifetimes of exploration. And when everything settles, I do not find myself standing before a wall, but before a clearer picture of our place in the universe. We are slower than light. Yes, slower than the very specific number 299,792,458 meters per second, a number fixed in the SI system since 1983. But that does not make us insignificant. It only says that we are part of a vast structure in which time, space, and energy are bound together by strict laws that have been verified for over a century. Ever since Albert Einstein published relativity in 1905, we are not free to do everything we can imagine, but we are free to understand what is really happening. And that freedom, to me, is what matters. When you understand why a limit exists, it ceases to be an annoying barrier. It becomes a natural feature of the world you live in, like the fact that Earth has a radius of about 6,371 kilometers, or that a year has 4 seasons, because its axis is tilted 23.5 degrees. You do not need to overcome those features to find the world astonishing. You only need to understand them. Our inability to reach the speed of light does not prevent us from measuring time dilation at the nanosecond level with atomic clocks, does not prevent us from observing muons living many times longer as they plunge from 10-15 kilometers altitudes, and does not prevent us from describing the curvature of space-time, first confirmed during the 1919 solar eclipse. Those things show that the wonder of the universe lies not in going really fast, but in how perfectly the pieces fit together, slower than light, but fast enough to understand why light matters so much. And when you reach that point, not by motion, but by thought, you can smile very quietly and say, "Ah, so that's how it is." If questions like these make you want to pause and think more about the universe you live in, please subscribe so we can keep digging deeper together. See you in the next conversation, where I want to join you in asking more seemingly simple questions that always take us very far.